Hello, my name is Julian Barr, and this is my lab report for Lab 2 of Physics 2211. In this lab, I analyzed the projectile motion of a tossed paper ball using video tracking and compared the observed motion to a physics-based model. The goal was to determine whether the motion follows the predictions of constant horizontal velocity and constant vertical acceleration due to gravity. Overall, the results showed that the horizontal velocity remains approximately constant, and the vertical motion followed a parabolic path consistent with gravitational acceleration. The system is the paper ball after it leaves my hand. The surroundings include the Earth, which exerts gravity, and the air. For the main model, I assume negligible air resistance, constant gravitational acceleration, g equals 9.8 meters per second squared downward, no horizontal forces. Using Newton's second law, F equals ma, horizontal motion, since there are no horizontal forces, ax equals 0, so horizontal velocity is constant. Xt equals x0 plus vot, where there is no acceleration included in the equation. This predicts a linear x versus time graph. Vertically, gravity acts downward. Fy equals negative mg. Velocity becomes Vy t equals Vy naught minus gt, and position equals y of t equals y naught plus Vy naught t minus 1/2 gt squared. This predicts a parabolic trajectory. We recorded a video of the paper ball
There we go.
and tracked its position frame by frame. The results showed x versus time was nearly linear. Y versus time formed a downward opening parabola. These match the theoretical model, which is designed using Python in GlowScript, as shown with this code in graphs. Small deviations likely came from minor air resistance, tracking inaccuracies, and camera angle distortion. Overall, the constant acceleration model described the motion very well. What does it mean? The terminal velocity occurs when the net force equals 0, meaning drag force balances gravity. In my no-drag model, terminal velocity does not occur because gravity is the only force, so velocity continues increasing downward. If drag were included, eventually F drag equals mg. At that point, acceleration becomes 0 and velocity becomes constant. In this experiment, the ball did not fall long enough to reach terminal velocity. To measure it, I could drop the ball from a much, much greater height and track velocity over a longer time to see the velocity graph level off. But what if the ball were thrown straight up? If the ball were thrown straight up with the same initial speed, it would take longer to reach the ground. In the original experiment, only part of the velocity contributed vertically. If it weren't thrown straight up, all the velocity would be just in the y component. Meaning time to reach the maximum height is simply t equals Vy naught over g. With a larger vertical component, the ball rises higher and stays in the air longer. Conclusion. This lab confirms that projectile motion can be separated into independent horizontal and vertical components. The horizontal velocity remains constant because there's no net force in that direction, while the vertical motion follows a quadratic relationship due to constant gravitational acceleration. The experimental data closely match the theoretical projections, demonstrating the validity of Newton's second law for projectile motion under negligible air resistance. Thank you for watching.